Okay, so here we have the live view of the sun as it looks right now. I'll give you an idea of what it is that I am using to observe the sun. So this is the telescope that's currently in my backyard. It's on a concrete pier. It's a equatorial style mount with a large 10-inch telescope along with a couple of refractors. And it's the refractors that are being used right now. So the live view that we're looking at first is with the white telescope on the bottom. And this system right here is what is allowing the view to be safe to look at. It's a Herschel safety wedge is the white thing here. And it's cutting the intensity of the sunlight by about 96%. And then inside of here, there's a filter that is blocking everything except a very narrow band of light in the ultraviolet part of the spectrum called calcium K. And then that's being fed into the camera here on the end. So that's what we are looking at presently. A little later, I'll switch over to the other telescope that's above it. This guy up here. And it is a hydrogen alpha setup. So it's a regular refractor, but there's a blocking filter that's tunable on the end, and then there's another blocking filter right here. And the two of those together give me a very narrow window of light down in the deep red end of the spectrum, which allows us to see some really interesting details on the sun. So going back to the live view.
And Jim, while you're making this presentation, we have a first comment or question from an attendee, Roger. Can
Sure.
you please talk a bit about your cameras?
Yeah, sure. I'll go back to the image. So both of these cameras, or actually all three that are in this photo, are all made by the same company. It's a Chinese company called ZWO. And they have made their name in the astronomical equipment business, making cameras especially for planetary imaging. So they're very affordable. They give good sensitivity and high refresh rates, and they work very well for doing lunar, solar, planetary imaging, and that's what I'm using. So the camera that's, I'll get my doodle thingy out here again. So this camera here that's on the hydrogen alpha scope, it's a monochrome camera called an ASI 290. And then this camera that is in the picture is actually not on that scope right now. It's actually over here. I'm using this camera right now on the calcium K view. And it's also a monochrome camera, an ASI 183. I like the monochrome cameras because they give much sharper detail and better contrast when looking at the sun and the moon, in my opinion.
And Jim, we have a second question in from Dennis now. Are the refractors used exclusively for solar observations?
No, these are generic refractors. This is just a, they're both William Optics, so it's a Taiwanese company. But this is just a simple 98 millimeter refractor. It's apochromatic, so it's a bit better quality optics. And then the upper one is called the Zenith Star 67. It's a doublet, an ED doublet. Quite affordable, actually. I bought that one used for about $300 off the internet. So I use these scopes for everything. I use it for lunar, I use it for deep sky, I use it for solar. They're just general multi-purpose telescopes. And it's the filters that I've added on that allow me to use them for viewing the sun. Okay, if there aren't any other questions about the equipment, I will go back to the live image. So this, as I mentioned, this is the calcium K view. So we're looking at a very narrow window of light down in the near ultraviolet range. I like using calcium K because it really highlights the surface detail. Now, the light that you see with your naked eyes coming from the sun is actually from a layer of the sun's atmosphere just below this one. This is what we see in the lower chromosphere, which is the layer just above the photosphere being the layer that we see with our eyes. That's where most of the visible light is coming from the sun. So I like this particular wavelength because of the details that we see on the sun. So right now we're looking at the whole disk, and you can see it's fairly quiet. There's just a little bit of brighter spots around, denoting where there's a little bit more activity, magnetic activity. Now I can zoom in to the full frame of the camera. So this is the full 100% zoom. I'm going to go down to this active region down here. So I don't know if you can see how much the atmosphere is bouncing around today. It's not too bad, but it's still something that you have to deal with when you're observing the sun. It's the Earth's atmosphere moving around. So these two bright regions here are an area where the sun's magnetic field is more concentrated, and it's changing the temperature of the material locally, making it appear brighter. If we follow these two spots for a few more days, they may turn into a sunspot. That's what people are hoping for, because sunspots are some of the more interesting things to observe on the sun's surface.
And Jim, as you say that, Caroline has submitted a question. Can you observe solar flares when they're happening, and what do they look like?
Yes, you can actually. A solar flare, to differentiate it from a prominence, a solar flare would be if these active regions where there's a concentration of magnetic strength, if it gets to a point where the material can no longer sustain that magnetic field, you can get a big release of energy, and that energy shows up as a very bright flash. So you'd see maybe this region here, for example, would suddenly go very bright. It would be saturated in this image, and that is what a flare is. So it's a lot of energy being released, and it happens in a very short period of time, a couple of minutes, and it would be gone. You can see it in calcium K. You can also see it in just visible light. If you just have a telescope with a white light filter, and Boyan will talk about that in the next segment. You can see solar flares in white light as well. I've only seen one in all of my career of observing. I know some of the other amateur astronomers in our group have seen them a number of times, or even caught them on a camera. Unfortunately, right now, the sun is in a low period of its cycle. It goes through a cycle of high and low alternating activity. And right now it's basically at the lowest in its cycle. So we don't see very many sunspots. We don't see very many flares. We see basically a bland uniform disk like this. So this is calcium K. I guess the last thing I wanted to point out was, I'll go back to 100% here. It's a little bit hard to see today because the activity it's pretty quiet, but there is a structure that the calcium K also reveals. If you look carefully, you can see there's the lighter areas outline these cells. It's kind of hard to see. I'm trying to highlight it with the yellow. So these threads of lighter areas, they are marking out the perimeter of these large, oddly shaped cells. And within those cells, there are smaller scale variations of light and dark. And this is actually marking out a physical distribution of hot and cold material. So the smaller granularity we call it is warm material is lighter in color and it's moving upwards, and the darker material is the material that has cooled and is moving back downwards, and it's like a convection cell. Like if you're boiling water on a stove, the hot water rises to the top and the cool water goes back down to the bottom. So that's actually what we are seeing here in this image, is warm material rising and cooled material sinking back down. The larger cells are that same convection, it's called, of material, but on a much larger scale. In fact, these cells are each roughly the size of the Earth, just to put it in perspective. So it's large areas of hot, primarily hydrogen, that's moving up to the surface of the sun. It cools down and then it goes back down around the edge. So it's another interesting thing I like to observe using calcium K.
And Jim, Dennis has asked a follow-up question.
Sure.
Does the atmospheric disturbance and shimmering change during the day?
It does. It has entirely everything to do with what the atmosphere is doing. So if the sun is high in the sky and there's a lot of heating of the ground, then normally this turbulence is worse. So morning time traditionally is the best time to observe the sun. That's when the air hasn't been and the ground hasn't been heated up much yet. But there is also a variation from day to day, depending on what the weather patterns are and what's happening in the upper atmosphere. So today I would say is an average day, maybe actually a little bit better than average at the moment for the Ottawa area. Okay, so I'm going to stop the share because I need to switch cameras now to the hydrogen alpha. If you give me a moment. There we go. So this camera has a smaller sensor than the other one, so we can only see a piece of the sun at a time. But I'll start by going back over to the area that we were looking at before. So that region that was a little bit brighter in the calcium K is actually this area here. Let me get my annotate tools back. It's this region right here. So that's the same spot on the sun's surface. So you can see the magnetic activity that we saw on the calcium K when we look at hydrogen alpha, which is, we're now looking at a layer of the sun that's above, physically above what we were looking at before. This is what it looks like. You can see it's really dancing around there today.
Jim, we have another question, and I'll comment to the person asking the question. It's come in through the chat room, which, as we warn people, we are not necessarily monitoring. Questions really should come in through the Q&A, but I've seen this one. So a person is asking, when you talk about the sun having hot and cold regions, what's the temperature difference you're talking about?
Yeah, that's a good question. So what we're looking at here is a little bit cooler than the previous camera, but it's all on the order of about 6,000 degrees Kelvin. Cooler areas that appear darker, maybe they're about 5,500 or as cool as 5,000 Kelvin, but still relatively hot. Yeah. So in this view, you can see the bright spot here and the bright spot here. That corresponds to what we saw in the calcium K. But we're also seeing kind of a swirling pattern around these spots. And that's the impact of the magnetism, the magnetic field lines coming out through those points, their effect on the hydrogen gas that's in that area. It's causing it to change its motion around those spots. If you occasionally see a dark smudge fly by, like just there, I'm not sure if with the compression you saw that. Sometimes you see dark shadows that fly across. Those are birds flying by, if you're wondering what they are. So the other interesting area today on the sun is over here on the other side. So we were talking a moment ago about flares, and there's often a confusion between a flare and a prominence. So a flare, like I explained, is a sudden release of magnetic energy that causes a bright flash, lasts a couple of minutes. And then there is something called a prominence. Let's get it better centered here. And I'm going to increase the exposure a little bit so we can get a good look at it. So this is a prominence, and it is hydrogen gas energized by the energy coming from the sun. So it's very high temperature. It's ionized, so it's hot enough that its electrons are stripped away, and it has left the surface of the sun and is drifting out into space, but it doesn't get very far before all the magnetic activity of the sun pulls it back down to the surface. And we see a bit of a looping pattern here, which is one of the different shapes that a prominence can have. Sometimes they look like a curtain, sometimes they're a loop. There's also even smaller little fingers of material. I don't know if you can see, there's a little little finger there, and you can actually see kind of like little hairs all along here. So that is also hydrogen that is leaving the surface, but on a much smaller scale. So this is actually, we're lucky today that we're seeing anything like this, as interesting as this, because prominences are normally associated with magnetic activity, and because the magnetic activity has been low for the last more than a year, there hasn't been a lot of prominences to see. So
Jim, as you talk about this live view you're seeing,
yeah.
Daniel is asking, can you talk about the exposure, gain, and gamma settings of your camera?
Sure. Let me just improve the contrast a little bit there. So right now I'm using an exposure of about 9 milliseconds. So each frame is 9 milliseconds of exposure, and I'm using about 1/3 of the available gain on the camera, which is what I would normally use. Any more than that, and the image starts to get a little grainy, which is fine if you're stacking after, but if you're just looking at it live, anything more than about a quarter or a third gain, I find is a little bit too noisy. It's a bit of a balancing act, because if you have too long an exposure time, then the blurring effect of the atmosphere with it dancing around worsens the view more than the graininess. So there's a balance on your exposure time to minimize the impact of the Earth's atmosphere, the seeing we call it, and balancing that with the noise. That's why I like the ZWO cameras. They use sensors that are relatively sensitive, so I can keep my exposure time low and still get a good image. So this, although it looks like it's fairly motionless, is actually in motion. And if we were to continue to watch this for, say, 10 or 15 minutes, we would see that it actually is changing on the order of minutes. And it's fun actually to take an image maybe every 15 minutes over the course of a couple hours, and then put that together into a little animation to see what this material is actually doing. Now, I'm going to go back down a little bit in my exposure. I'm going to show you something.
Jim, we have another question from Tom. Do these prominences have a consistent distance from the sun before being pulled in? Does it vary depending on the underlying surface and temperature?
Yeah, there's a lot at play there. It depends a lot with what's going on in the magnetic field of the sun. Because this material is ionized, so it's positively charged, it can be, its motion is affected by magnetism. So depending on what's happening in the sun's magnetic field in that area, it completely affects what happens with the material. Sometimes the material has enough energy that it will escape. It just goes straight off into space and it never comes back. Other times it only gets a little bit above the surface before returning. Like if you see all the little, you might be able to see this band now better. Sort of there's a, between the arrows I'm drawing here, there's a band. And that's all same idea as a prominence, but very small scale. And it only goes, that's what, on the order of 1/3 of the Earth's diameter, maybe, distance, before cooling down and falling back. It's only in the area of higher magnetic activity where the gas gets enough energy to go far from the surface that we see a prominence like this. So what I did want to show you, can't really see very well anymore. It was better earlier this morning. because I think it's because the sun has moved. But I'm not sure you can see there's a dark patch right here, a bit darker area. This is actually part of the same blob of material. It's part of the same prominence. And you often see dark strings like this across the face of the sun. And we call them a filament when it's on the surface, and a prominence when it's visible on the edge, but they are essentially the same thing.
We have one more question, Jim, and then I'll warn you that you're at 10:29, so basically time to transition. But Dennis asks another question. At lower exposure, the 3D aspect of the solar sphere is evident. Why is that? Seems strange when it is the light source and a very strong one.
You're probably talking about something called limb darkening. I don't know if we can see it in H alpha because we can't see the whole disk of the sun. Let me bring the exposure down. Yeah, it's not as prominent here. When we were looking at, here, let me, I'm going to switch my share over to a still picture again. And I'll show you an example. So in this image, there is quite a noticeable difference in how bright the sun looks from the center to the edge. It gets darker. And that is entirely due to the fact that the sun is a sphere that's radiating energy into space in all directions. And when you look at an object, even if this was just a ball bearing that you had heated up and you're looking at it with an IR camera, it would look the same. And it has to do with the fact that the photons coming from the sun in the center are coming right at us, but the photons over on the edge are not coming right at us. They're coming at us at an angle. And as a result, we see fewer of the photons from the edge than from the middle of the disk. And it gives it that gradient. We call it edge darkening. Hope that answers your question. And I think that is it for me for now.